Okay. Oh, again, somebody stole my cheese. You mean we're still in the, oh, that's series 4. We're not out of series 4 yet? Oh, is that the e to the ix one?
Yeah.
Oh, okay. This is one of the most beautiful problems in all of mathematics. Look at this. Okay, you start by writing the power series for e to the ix. Okay, what's the power series for e to the box? 1 plus box plus box squared over 2 factorial plus box cubed over 3 factorial plus box to the 4 over 4 factorial plus box to the 5 over 5 factorial plus box to the 6 over 6. There's a reason I'm doing this many. Box to the 7 over 7 factorial plus dot dot dot. And then you simplify it. Wasn't that part of the problem? You're supposed to simplify it? Okay, so go. Yep. I'll do the first term. 1. In fact, I'll do the second term too. Ix. And then?
Minus x squared over 2 factorial. Minus ix cubed over 2 factorial. Plus x to the 4th over 4 factorial. Plus ix to the 6th over 5 factorial. Minus 6x to the 6th over 6 factorial. Minus ix to the 7th over 7 factorial.
That is correct. You guys know how I got that? Or how? Because I squared is -1, right? I cubed is -I, and so forth, right? Now, when you work with complex numbers, you always work with the real part and the imaginary part separately. So, if you look at all the real parts, in other words, the things without the i's right here, look at the real part. Let's write it up. Why do I hear crinkling? 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. And then, look at all the imaginary parts, the ones with the I. If I factor out the I, what's left? X minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. And then you stand back and go, hey, you somebody! And then, you somebody! So this is equal to cosine x, right? Plus I, and that's equal to, hey, you somebody! That's sine x. And then, you somebody! That's kiss x. So what did we just prove right here? We just proved that e to the ix is equal to kiss x. This is Euler's formula. Remember this came up when we studied polar? Of course not. This is a very powerful, so that means you can raise e to any number, even imaginary numbers. Actually, your calculator can do it, you know. Okay, so for example, e to the I pi, what is that equal to according to this? According to Euler's formula, e to the I pi equals kiss pi. But what does kiss stand for? Cosine theta plus I sine theta. And then what is cosine of pi? -1, and then sine of pi is 0. Also, e to the I pi is -1 then. Yeah, try to just do it on your calculator, just because you guys don't believe me. Punch this in on your calculator. E raised to the I pi power. Boom! Your calculator just spits out -1. Yeah.
Well, what's the other Euler thing?
Euler's law.
Oh yeah. Correct. Wait, does that mean Fibonacci has a series too?
No.
Yeah, it's a sequence.
Yeah. I'm sure he had some series, but. So did it come out to -1? Yeah, your calculator can do stuff, you know. Besides add and subtract and play games. So what did we just show in this problem? E to the I pi power is -1. Now watch this. I'm going to add 1 to both sides, and this is one of the most beautiful equations in the history of the universe. E to the I pi plus 1 equals 0. Just adding 1 to both sides. Why is this equation so famous?
This got E, I.
Exactly, it has the 5 most important numbers in mathematics all in one equation. Yeah, 0 and 1, like this is the identity element for addition, this is the identity element for multiplication, and of course E, I, and pi, right? Doesn't that bring tears to your eyes? Anyway, those of you going on to AP Physics C next year, you better remember this. This is, you need this to analyze alternating current and stuff. E to the IX equals KISS X, very important. Or if you're going to do engineering in college, oh, yeah, but of course you're going to go to college and go, oh, we never learned that in high school. My pre-calculus teacher didn't teach me anything. Okay, next, we took care of number 9. Now we're finally on series 5. How come there's series 6 up there? Series 6 is not even the homework. Come on, we had a holiday yesterday. Okay, series 5. Number 1. Roll my eyes at that one. Okay, let's do it. We gotta do it. Because this is definitely on the test. Okay. Y, now if you haven't figured this out by now, I only can give you either y equal x squared or y equal x cubed, right? That's the only ones I can give you. How come? Because those are the formulas we know. What are you talking about, Mr. Park? I can only give you y equal x squared or y equal x cubed. Unless I think of something. Okay, now, in your homework or when we did the example on the board, what did we do? 0 to 1, yeah? So I go 0 to 2, all hell breaks loose. Obviously. Okay, you break this up into n rectangles. How far is it from 0 to 2? If I break that up into n equal parts, each part is going to be 2 over n. So that's 2 over n, 4 over n, 6 over n, all the way until you hit 2n over n. Then you make the rectangles just exactly like they did last time. Circumscribed rectangles like this. Okay, what's the area of the first rectangle? Base times height. 2 over n is the base. What's the height? The y coordinate at that point. 2 over n squared. Then you move over to rectangle number 2. What's the base? 2 over n. And the height is the y coordinate of that point, which is 4 over n squared. And then the next rectangle, the base is 2 over n. Hey, Mr. Park, they're all 2 over n. Yeah! It's the length of this divided by n, right? And the height is the y coordinate at that point, which is 6n over n squared. And then you just keep on going till you hit the last rectangle. What's the base? 2 over n times the y coordinate at that point is the height, 2n over n squared. So, what if on the test I ask you 0 to 3? What are you going to do? Then what's the only difference going to be? 3 over n now, right? Okay, now here's the hardest part for you guys, I think. Because I think last year I did 0 to k. Is that going to throw you off if we put a k there instead?
No.
What can be factored out? 8 over n cubed. What? Okay. What's left? 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared. See, if it's x squared, then you're going to have the sum of squares inside here. If it's cube, you're going to have the sum of cubes, right? We know those formulas. That's why I can only give you x squared or x cubed, unless I do something. 8 over n cubed times a. You somebody. Wait, let me look at my notes, I forgot it. N plus 1, 2n plus 1, all over 6. So this is the formula for the area of n rectangles, but we don't want an estimate, we want the exact value, so we take the limit as the number of rectangles goes to infinity. And do we know how to compute a limit? If the degree of the top is the same as the bottom, you look at the coefficients, 16 over 6, 8 thirds. So this area is exactly 8/3 now. That is not an approximation anymore. It's exactly 8/3 square units. So, when you do this problem, inside, after, whatever you factor out, I'll give you a hint. You know, some of you, Mr. Park, I don't know what to factor out. I'll give you a hint. You factor that out. Because that's how you get 1 as the first term. You get it? Because the first term gotta be 1 squared or 1 cubed or whatever, right? Inside this parentheses, it's either gonna be 1 squared plus 2 squared plus 3 squared to n squared, or it's gonna be 1 cubed plus 2 cubed plus 3 cubed to n cubed. Unless I give you something else. Okay, next, number 5. Whoa, you guys could do 2, 2, 2, 4. By the way, I'm just curious. Number 3. How did you guys do the power series for cosine squared x? I'm just curious. Did you guys cosine times cosine like a maniac, or did you use like an identity, a shortcut? Anybody use the shortcut? Time. Clock. If there's an identity, there's a shortcut. Otherwise, you're just gonna do long multiplication. But I like that, Mr. Park. It's fun. Okay, you can do that. However, cosine squared x. Okay, I don't want to do long multiplication. Where have I seen cosine squared x in an identity? 1 minus sine squared x? But that's more work! You want an identity where you do less work. How about this? Cosine 2x is equal to 2 cosine squared x minus 1. Remember this, a double angle identity? So by solving for cosine squared, what is cosine squared x then? Move the 1 on this side. 1 plus cosine 2x all over 2. Oh, so all you gotta do then is go 1 plus, what's the power series for cosine box? 1 minus box squared over 2 factorial plus box to the 4 over 4 factorial minus box to the 6 over 6 factorial plus dot dot dot, and then just divide the whole thing by 2. You don't have to do any long multiplication. But then you gotta know your identities, which could be a problem, yeah? I'm just doing long multiplication and division, Mr. Park. Okay, whatever. I'm just giving you an alternate way. Okay, number 5. Number 4, you guys did. How did you guys do number 4? Did you guys use the binomial theorem, or did you do long division? Okay, whatever. And then number 5. Well, how come you can do 4 but not 5? I'm just curious. I don't know, that's just the way we are, Mr. Park. Number 5. 1 minus x squared to the what? Negative 1. Okay, so this one you're not going to do a binomial theorem because these are 3 terms. You got to use the trinomial theorem. You guys don't even know the binomial theorem. How you can do trinomial theorem? Anyway, negative 1 power means 1 over, right? And what does this bar mean? Divide, so you got no choices, so you got to do long division. So 1 divided by 1 minus x squared. Now this is a beautiful problem. You guys have your tissues ready? This is going to be beautiful. How many people did it? So you guys all cried out already, right? You 2 people. 1 goes into 1 how many times? Okay, then multiply by the divisor. 1 minus x squared. Subtract. X plus x squared. 1 goes into that how many times? X. Okay, multiply x times x minus x squared minus x cubed. Subtract. 2x squared plus x cubed. 1 goes into that how many times? 2x squared. Multiply. 2x squared minus 2x cubed minus 2x to the 4th. Subtract. 3x cubed plus 2x to the 4th. 1, see, when this number is a 1, it's easy to do long division because 1 goes into, come on, 1 goes into that how many times? 3x cubed, multiply that times the divisor, 3x cubed minus 3x to the 4th minus 3x to the 5th, subtract 5x4 plus 3x5, 1 goes into that how many times? Plus 5x to the 4. Hey, you somebody! That's the Fibonacci sequence. The coefficients are the Fibonacci numbers. 1, 1, 2, 3, 5. What's the next one gonna be? 8x to the 5th, then it'll be 13x to the 6th, then it'll be 21x to the 7th. Isn't that beautiful?
So he has a sequence.
That is the Fibonacci sequence.
Oh yeah, series. Never mind.
You don't call this the Fibonacci series. The coefficients are Fibonacci numbers. That was just beautiful. Okay, number 6. Oh, how many people got this one? This is another one that's going to be serious, guys. Only 2 people did it. What's a partial fraction? Is that the question? Some of you just reading it now, yeah? Oh, baby. You guys don't know. See, you guys don't know what you're missing when you don't do the homework, Hanaoka. I designed these problems. I put these problems in the worksheet, so when you do it, you go, oh my God. And you have an epiphany.
I kind of just try to get the right answer and match it to the bottom.
Oh, no, that's not mathematics. I don't know what that is. Sigma. N equal 1 to infinity, what is it? 1 over 4n minus 3 times 4n plus 1, is that right?
Yeah.
Okay, now, we can do it by looking at the limit of the sequence of partial sums, okay, but I want you to do it by decomposing it into partial fractions.
What's that?
So, do you guys remember how to decompose into partial fractions? Does this sound familiar? The Heaviside method? Equating the coefficients? Even in AB you gotta know this. This is not just BC topic, this is BC and AB. Okay, so what fractions when and this is an easy one. What fractions when I add them together will give you this? Use common sense. Something over 4n minus 3 plus something over 4n plus 1. Does that make sense? If I add these 2 fractions together, that's what you get. Okay, now how do I figure what A and B are? What do? You either use the Heaviside method or equating the coefficients. Okay. So what's the first step? Multiply both sides by the LCD to get rid of the fractions. Okay, let's use Heaviside method because that's just way easier. Okay. What number can I plug in for n to cancel out one of the terms?
3/4.
Okay, 3/4. If I plug in 3/4 for n, you're gonna get 1 equal.
Oh gosh.
I'll give you a hint. 4 times 3/4. The 4's cancel out.
4 is 1.
What? Yanamari, you can't handle that. Hanaoka, plug in 3/4.
3 plus 1. 4.
Okay. And then if you plug in 3/4 there, it gets 0. Oh, we just figured out A is 1/4. This is called the Heaviside method, named after the mathematician
Heavy.
Oliver Heaviside.
Heavy. How come his name's not French or Greek or like your
I believe Oliver Heaviside was an English mathematician. He's from England. Okay, what's another good number to plug in for n? Negative 1/4, because then it's going to make this one 0. So you get 1 equals 0. I'm afraid to ask. Plug in negative 1/4 here.
Colin something 4 minus 3. Too many.
Negative 4b. So b equal negative 1/4. Oh, so Mr. Park, this problem stay the same as what is A? 1/4 over 4n minus 3 minus 1/4 over 4n plus 1. All I did is just decompose it into the partial fractions. Everybody see that? Okay, now you ready? You got your tissue out? This is so beautiful. You're gonna weep. How can you not weep when you see this? Okay, now here we go. Plug in numbers. Here we go. Plug in numbers. Go. Plug in 1. 1/4 minus 1/20. Okay, but you did it already. What about the people who didn't do it? Zion, you did it?
1/20.
Whoa. Okay, plug in 2. 1/20 minus 1/36.
136.
Okay, 1/36 minus, we're plugging in 3 now. It's 13, so 1/52, is that right? Yeah, let's just do one more, just for a good measure. Plug in, what are we plugging in now? 4. 1/52 minus 17, 1/68 plus dot dot dot. It goes on forever. What do I do with this, Mr. Park? Well, look at, do you see the beauty of it? Look. This cancels that. 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 All the way to infinity. What's the only thing left? 1/4. Isn't that beautiful? Okay, next problem. Come on, you gotta admit, look at the beauty of that.
Who's that problem named after?
It's not named after anybody, it's just a technique that you're using.
Oh, so you made that one up?
Well, once you know the technique, then you can make up any other problem, right? Okay, next. What was that, 6? Okay, 7. Okay, are we really doing 7? Apparently. Okay, find the interval of convergence. Okay, now, if I ask you what the interval of convergence is, what kind of series does it have to be?
Geometric.
It has to be geometric, right?
Yes.
Okay, it has to be. Next year when you take BC calculus, however, then it's not going to only be geometric. Now, in order for a geometric series to converge, what has to happen? The absolute value of r has to be less than 1, right? This is how you find the interval of convergence. So, all you have to do for this problem on the test is you figure out what the common ratio is and you put that right there. Okay, now look at that problem. What is the common ratio? 2 sine x, the thing in the parentheses, right? Solve this inequality, that is your answer. That gives you the interval of convergence. Okay, now how do you solve an inequality like this? Absolute value of gorilla is less than banana. You put the gorilla in the middle, and what do you put here and here? Negative banana and banana. Divide by 2. And then what? Divide by sin? No, now you gotta think. Where is sine x between negative half and a half? These are numbers you're supposed to know for. So, maybe for you, it's easier to think of the unit circle. Where is sine either plus or minus half? So you gotta get your pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. Now, where is sine gonna be between there? Where is the y coordinate between negative half and half? Like over here and over there. And then you just write that down. If you look at the answer on the bottom. I think I used the k-pi notation. But like I said, if you don't know how to use the k-pi notation, just write it out and put dot dot dots on both ends, right? Like right from negative pi over 6 to pi over 6. Or from 5 pi over 6 to 7 pi over 6. Or from 11 pi over 6 to 13 pi over 6. And then put dot dot dots on both ends if you don't know how to write the k notation. Mr. Parker, I don't like trig. Then you're not going to like calculus. Calculus is almost all trigonometry, logarithms, and e to the x stuff, you know, that you can. That's why we study it. And finally, the last problem. 2 to the n over n from 1. Okay, 2 to the n over n factorial, sigma n equal 1 to infinity. Now, probably on the test, I'm going to tell you how to do it. Like on the test, I'll probably give you hint, this is a power series. See, but in the old days, there was no hint. I just give it and you gotta know this is a power series. But for you guys are special, so it's gonna say, hint, this is a power series, which means it can only be one of 5 power series. That's you only gotta know. So what should I do then? Write out the first few terms. Plug in 1, 2, 3, go. 2 to the 1 over 1 factorial plus 2 to the 2 over 2 factorial plus 2 to the 3 over 3 factorial plus dot dot dot. So, what is the only power series that has the consecutive numbers factorial in the denominator? E to the box, right? So, this is what you should do. E to the box equals 1 plus box squared over 2 factorial plus box cubed over 3 factorial plus dot dot dot. What number do I have to put into the box to get these numbers there? It rhymes with move. 2! See, look, 2 cubed over 3 factorial. So if I plug in 2 into all of the boxes, hey, it's e squared! Except we have a problem, Houston. Houston, we have a problem. There's no 1 there. So Mr. Park, you're just asking us to find this then. Well, duh, then subtract the 1 on this side, and that's why the answer is e squared minus 1. That's called loamy.
Do you have to factor that?
What do you mean factor? No, the answer is just e squared minus 1. You mean e plus 1 times e minus 1.
Yeah.
No, what the person even does that kind of stuff? E squared minus 1 is the answer. So that, see, this is telling me we don't even know our power series.
Factor?
Okay, here. I'm just gonna pick one person at random.
Oh,
Let's see. Who is it gonna be?
No.
Yoshina. What is this equal to? See the eyes going down, looking at the notes. It should be at the tip of your fingers. Hint, this is a power series. What? Okay, so what number do I have to plug in for x?
1,
Okay, so therefore,
natural log 2.
that's natural log 2. Woohoo! You guys get it? That's the power. Okay, what's the power series for natural log 1 plus x? I don't know. Let me look at my notes. Minus x. That's so shady. What number do I have to plug in for x to get these numbers here?
1.
Yeah, Yoshina said it 1. So if you plug in 1, you get natural log 2. In fact, this is how you compute natural log 2 in the old days. You just keep on doing this like all year long. At the end of the year, you get your answer. That's an approximation for natural log 2. Oh boy. Okay, last thing for today. Oh my gosh, I thought we were gonna finish early. Was this the class? I asked one class to think about it. Was it? I don't know. This is a very famous. There are a lot of famous series in mathematics, people. If I were to keep adding this, by the way, this is called the harmonic series. If I keep on adding these numbers forever, what do I get? Anybody want to take a guess? Natural log 0 is undefined. Okay, this is what period, I think, was this the class I showed you this? Okay, it was period 6 then.
2.
Okay, see, that's what Al said. You're in the same boat as Al then.
Is that good?
Well, I'll give you a hint. If you just add the first 4 terms, that's bigger than 2.
Infinity.
Well, infinity is not a number. Okay, so if it is an infinite sum, then we would say this series diverges to infinity. You don't say the sum is infinity because infinity is not a number. Okay, let me just tell you, okay, what I'm gonna do is I'm gonna compare this with a series that I know. Okay? What if I were to add an infinite number of halves together? Forever. keep on adding half plus half plus half plus half forever. What do you get? Okay, this is what somebody said like 6 years ago or something. They said 500. Because they thought 1,000 was the biggest number. No, this series diverges to infinity, has an infinite sum. Does everybody agree with that? Okay, now what I'm going to prove to you is this series is bigger than this. That's what I'm going to prove. If I can prove to you that this series here is bigger than that, then wouldn't this one diverge to infinity also? Because what's bigger than an infinite sum? Another infinite sum, right? So if I can prove to you that this is bigger than that, then that one diverges to infinity also. Okay, watch this. This is beautiful now. Okay, would you agree that 1 is bigger than a half?
Yeah.
You took that long to figure that out. Would you agree that 1/2 neutralizes that half? Okay, now here, this is where it starts. If I add the next two terms, that's bigger than a half.
Yeah.
Without actually adding that, because some of you are going, oh, these common denominators, 12. That's 7/12. Yeah, that's bigger than a half. No, but think like this. What is 1/4 plus 1/4? A half. But since that's bigger than 1/4, gotta be bigger than a half.
Oh.
You know what I'm talking about? Okay, now look at the next 4 terms. By the same reasoning, that's bigger than a half. Because what's 1/8 plus 1/8 plus 1/8 plus 1/8?
1/2.
1/2. But these 3 numbers are bigger than 1/8, so gotta be bigger than a half, right? Catching on? So what's gonna be next? I guess we're not catching on. The next 8 terms, that's bigger than a half. By the same reasoning, and so what's next? The next 16 terms, that's bigger than a half. The next 32 terms, that's bigger than a half. The next 64 terms, that's bigger than a half. Yeah, but Mr. Park, that's unfair. You're teaming up on them. You're going 4 against 1, 8 against 1. Yeah, but you can do that when you have an infinite number of terms. So, what did I just prove to you? I proved to you that this series is bigger than that series. So if this diverges to infinity, that diverges to infinity. So what did we just learn today? A harmonic series diverges to infinity. Those of you in physics, every year they tell me, Mr. Park, we did that problem in physics. Something about stacking the books. Who's in physics? Something about if you stack the books. Is it going to tip over or not tip over? Okay, just look away if you know. Okay, so how would you write this harmonic series in sigma notation? N equal 1 to infinity. How do you write it? What's the explicit formula? 1 over n. Now, the harmonic series is a specific case of what we call the P-series. When you have n to the p there, we call this the P-series. So when p is 1, we call that the harmonic series. And see, the harmonic series is like the border between diverging and converging. So, if you look in your notes, the P-series, if p is less than or equal to 1, the series diverges. But if p is greater than 1, the series converges. Converges means it adds up to some finite number. Diverge means it doesn't add up to some finite number. So the harmonic series is the difference between converging and diverging. For example, okay, what if I give you this then? 1 sigma n equal 1 to infinity 1 over n squared. In other words, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. Keep on adding forever. Now, does this series converge or diverge? How do you know? Because 2 is bigger than 1. That's right. What about this? Sigma n equal 1 to infinity 1 over the square root of n. So 1 over root 1 plus 1 over root 2 plus 1 over root 3. If I keep on adding these numbers forever, what happens? It diverges to infinity. How come? Yeah, because this is like n to the half power, and half is less than or equal to 1. Yeah? See, so if the terms get closer and closer to 0 fast enough, it converges to some finite number. But if it doesn't go to 0 fast enough, then it diverges to infinity. But the harmonic series right here, that's like the order between converging and diverging. Now lots of times, see when you take BC calculus next year, you have to determine whether a series converges or diverges. Now sometimes we don't know what it converges to, we just know it converges. Like this series here, do we know what it converges to? Yes we do. This is one of the most famous series in mathematics. Chive. Clock. Okay, I'll tell you, it's pi squared over 6. If you keep on adding these numbers forever, Euler proved that you get exactly pi squared over 6. Euler has many things. In fact, he published the most amount of mathematics in the history of the world. That's why he's number 4. Okay, anyway, I just wanted to expose you to the P-series. Question.
So if it's P-series, what is short for power series? You just say power series? Or can you say P-series for power series?
No! No! P-series is this series right here. This is a P-series. A power series is one of those 5 you're supposed to memorize. A power series is an infinite polynomial. This is not, these are just numbers here.
So there's nothing short for power series?
No. Any other dumb questions? Okay, we're done. I thought, oh man. I'm just gonna have to watch the video.
I don't know what it is.
Anyway, I heard on ESPN, there's no such thing as dumb questions. Just dumb people asking questions.
What?
You never saw that commercial?